technology. Last time we talked about transformation, but what is it that's driving this transformation? So we're going to talk about the technologies. The journey that we're going on is, first we're going to define what these technologies are, how they work, what are the implications, give you some examples, and how does this shape our future? And so our age is shaped by pervasive computing, but there's computing all around us, so we all have access to wireless mesh. You don't need big infrastructure network systems in order to connect. Biotech, healthcare, where's that going? Machine learning. Now, people get machine learning and AI mixed up. I'm going to focus on machine learning. Basically, the things on your phone and everything else is about machine learning. AI is basically the larger set of it, and AI has more to do with how machines mimic humans. So we're talking about emotion and speech recognition, detecting sarcasm. Not that I would ever do that. Those kind of factors. Nanotechnology, we're still in the age of materials. 3D printing, which is all around us. Robotics. And finally, super tech. And those technologies that in general have larger applications. So how did I pick these technologies? Well, one is intelligence, meaning can it act on our environment? The next is fit, and that's is it relevant to human schemes, and how widespread is it actually? And so how does it impact things such as commerce, health, or the environment? And health was so important, I accidentally put it down twice. Pervasive computing. These are things like blockchain, IoT, the cloud. And so it needs ubiquity. It needs to be wherever we are. The barriers are brought down. People can afford it. How does it transform us? How does it unlock new capabilities? And finally, how does it what's on the horizon? And so naturally the big push right now is towards smart cities, microgrids, and telemedicine. Another kind of pervasive computing people don't talk about is actually search, because that's a big part of what we do when we're on computers. Excuse me. So who's number one in vacation rentals, Airbnb or tripping? Well, you look at that and say, gee, Dr. Joe, you're trying to fool us. Okay, well, I wasn't trying to trip you up. Ba-da-da-boom. But Airbnb has 2 million bookings a year, and tripping, 8 million. How can this have so many more bookings? And I've never heard of them. Well, tripping is what they refer to as meta searches, meaning tripping actually searches the search engines. And so it searches Airbnb, VRBO, HomeAway, all of them. And that's why naturally it's going to be bigger. So the keys that we see here are again these techniques of the value chain and zooming. And that's that you go bigger or you go smaller. And the way you can measure it is the value chain. Look at the activities. Wireless meshes means that we have so many devices that are connected right now. You don't need a big hub and spoke type network, but you do need one connection to the internet. But from this one connection, you can connect everyone else. And this replaces the hub and spoke model, but for emerging nations or for emerging businesses, they have this opportunity of not having to put in this big upfront purchasing. And so right now we see big global initiatives for this and wireless mesh networks, and they affect many, many industries. Biotech. What's driving biotech right now is genetic engineering, cell technology manipulation, so this gets into all the DNA stuff, and also digital technology. It tries to be preventative instead of reactive. We don't wait for diseases to exist. We try to go up against them right away. How does this work? Well, the way it works is that your cells or whatever identify a problem, and then your body attacks it. Now, you could have bad encoding, meaning your body will attack itself for no reason at all, and that's the nature of diseases like multiple sclerosis or lupus. Now, in terms of cells attacking each other, um, this is why we have no vaccine for AIDS, and it's because the HIV cells, the proteins mutate over time, so it's hard to pin it down exactly what the body should go after. We're in the age of biologics, and that's that our drugs are based on biological materials. Humira, Enbrel, a lot of the rheumatoid arthritis drugs are biologics. Gene therapy, we're working on creating new drugs and everything else by manipulating the genes around. Biomarkers have to do with food, and that's that we look at things that make us sick in food, or we put in ID implants. Basically, what we're trying to do is identification in general to try to find what certain things are happening. And finally, immersion is wearables, especially with Apple. How can I forget Apple? Getting EKGs permitted. You can know your health 24/7 of what's going on with you. And so these are the technologies. Oh, and not only that, but your doctor has that information. These are the technologies that drives biology. Now, 3D printing, you've all seen it. 3D printing is basically you just put down a layer of material in a pattern, and then you keep layering and layering, layering, layering until you get what you want. It's not just for plastics and toys. This is where 3D printing is evolving. And the key advantage to 3D printing is customization, that every time you do a run, you can change the specification. It's not like setting up an injection molder that has only one kind of mold in it. And so they're trying to find more applications for it, such as concrete, ceramic, pills. The layers get thinner and thinner, and so what they're trying to do is increase the precision. Right now, in technology, you've got a gap. You have a gap between you could put down angstroms worth of film. And this is what the semiconductor industry does. However, in order to get that level of atomic purity, you need to do it under vacuum. And so, but vacuum is an expensive process. And so the non-vacuum processes are trying to catch up to the vacuum processes. And so the other implication of 3D printing is it's cheap. It doesn't take up a lot of floor space. You can make a mini factory in your garage. However, the problem with 3D printing is it's great for prototyping. For example, prototyping drugs, if you can make drugs with it. But the problem is every other technique can give you scale. You can make millions of it for very cheap. No matter what 3D printing does, it's not going to catch up to injection molded plastic. But there is a place for it. Machine learning. The drivers of machine learning are the cloud, big data, and AI. And so the reason why we can implement machine learning is that since it's in the cloud, that means it can touch everywhere. And big data of understanding how to process data, algorithms. This is what defines machine learning. And subsequently, it's created the field of data analytics. We can interpret what different things do, meaning based on certain data, how should I react? And so now we're talking about control. Nanotechnology is when you talk about materials in the nanoscale range. To keep it in perspective, of 1,000 angstroms, medium-sized atom is about 20 angstroms, so you can put that in perspective. What it comes down to is in order to pull off nanotechnology, you need chemistry, you need process, you need tools. And people don't talk about tools enough. But if you're going to build this at scale and you want to do it repeatably and also cheaply, you're going to need tools. And so in terms of coatings, for example, this is what a semiconductor chip looks like. And so as you can see, you have anywhere from 7 to 15 levels of interconnect metal on top of your chip. So you have all the semiconductor stuff down here. But all these billions and billions of transistors have to connect with each other. So you need metal lines to do that. Well, how do you connect from here to here without shorting and things like that? And so you put it up in layers. And actually that isolation layer between the metal If you notice, it's very flat and planarized, which is not an easy thing to do when you have all this topology and everything stacked on top of each other. Dr. Cho worked on that in the 80s. Yeah, what was an electrical engineer working on a materials project? Yeah, that's what happens when you have good generic skills. Anyway, some other coatings. Lululemon, a lot of these yoga clothes, they talk about being antimicrobial and also anti-static. Actually, that technology has been around for a while. Nobody occurred to anybody to apply it to like yoga clothes. How do I know this? Because I know the scientist who actually invented the technology, and he did it for DuPont. He used macroparticles, integrated silver, and it was actually intended for the printing industry. They used to do, long rolls of printed material. And who was that scientist? Dr. Thomas B. Cho, my father. He's long gone, but I don't know how he would feel about it. Anyway, drug patches. Who came up with the first drug patch? UCLA. But drug patches are a big deal for drug delivery. We make things better for us. And then you have things like Under Armour coming up with new materials. And what is Under Armour trying to come up with? Bioceramics. First, they're trying to cool you off, but the other way they can cool you off is, why are you getting so warm? You have two sources of heat. Internally, meaning from you ingesting calories, and also from the atmosphere. And so what they're trying to do is come up with a coating to reflect heat. So this is what's going on in nanotechnology. The atom and understanding the atom, and this is why I've never been big on Einstein and much more on Bohr and Heisenberg and people like that who worked on the atom, because our age is defined by the atom, whether it's the bomb, the semiconductor, the integrated circuit. But once a new material comes along, that creates a whole set of innovation. And so what is our next big challenge in the future? We want technology to form around us. And so also we want to find new materials to give us a cleaner world. And so nanotechnology is very much a field of interest. Robotics. You've seen all the factories. The thing is, robotics now is very precise, tight tolerances. It's agile and it's intelligent. It's able to apply information. You can give it rules in order to act in. The thing about robotics is, what is it as a field? It's multidisciplinary. You need to know something about electrical engineering, mechanical engineering, and software. The center of that is being able to do everything in robotics. What do we use it for? Repetitive tasks, high-risk tasks. The challenges, the reason why it's taken this long for robotics actually has been processing. The processors weren't fast enough and there was too much code in order to perform certain actions. And so ultimately you're also going to need a human interface. Some things that are not going to happen in robotics and miniaturization. No, we're not going to send robots down your arteries and all that's going to attack and do things, and we're not going to have intelligent flying little robots. Actually, the military approached me to go work on that back in the 90s, and part of the problem is just the amount of processing, and it can be interfered with. That's part of the problem. Not only the mechanical aspects of it. The digital technologies that define our age summarizing are basically devices, Internet of Things, security we're very much concerned with, AI, blockchain, and also the cloud. The thing about the cloud, as we talked about in the last lecture, is that we could be connected to pretty much any computing, and it's all because of the cloud. Excuse me. And not only that, the cloud is very much a very big part of security. That one of the safest ways you can protect your data is to put it in the cloud, because the way the linkages are set up, they can get some of your information, but not all the information. And so we'll continue this in the next video.